Now, there is the very important concept what is known as the goodness of fit. So, what is the goodness of fit? So, basically, goodness of fit, to understand this concept, let us go a little back here. So, we wanted to find out the relationship between y and x. Now, since we do not have the population data, or we cannot obtain the population data, we take some sample. Now, once we take the sample, we estimate this relationship using those sample observations and try to find out, or try to find out the, or try to take the inference about the relationship among the population. So, what we do here, that let us say here we have this x and here we are having y, then we have certain sample observations here. So, these sample observations we have, then using OLS methods, we wanted to estimate a regression line like this here. So, this regression line is nothing but we have y hat is equal to beta 0 hat plus beta 1 hat and x1 here. So, this is the estimated regression line we have. Once we have that estimated regression line, then the natural question comes is this: how this regression line fits the data. So, when we say fits the data, basically we mean that how much there is the variation among these sample observations from the estimated regression line. If there is the less variation, that means it fits well. If there is large variations, that means the fit is not well. Let us say if we have another scenario where we have same x variable and we have the y variable here, and let us say we have this data here, and the estimated regression line goes like this. So, here we can see there is a very few dispersion we have, that means this fits comparatively better than this particular here. So, if you are able to see here, so basically what we wanted to know here, how much variation of this the population parameter population is able to explain by this estimated regression line. So, when we say how good it is fits, so basically we wanted to observe how much total variation is being captured by the estimated regression line. And that's the basically concept of goodness of fit, which often represented by R square. So, what we can say, that means that it measures the proportion of the variation of y explained by the x. Or in other sense, we can say it is nothing but explanatory power of the regression line. So, when we say how good it fits, that means basically we wanted to know how much variation of y is being explained by the estimated y. We basically want to know how much variation of y is being explained by the x. That's the question we are asking. Now, to understand that, to formulate the mathematical formula for that of this goodness of fit, which is often represented by R square, so we can think of this way. In deviation format, what we know this y is equal to y hat plus u hat. Now, what is this y? This y is nothing but y minus y bar, that is deviation from the mean, and this y hat is basically nothing but the estimated value and the deviation from y bar. Why? Because we know that from the properties of this, expected y hat is equal to y bar. So, therefore, we are using here this, and this u hat is nothing but the difference between the estimated value and this y. To understand this, let us think of this way here. here we have x, and here we have y, and here we have this estimated regression line, which is basically, here we have this y is equal to beta 0 hat plus beta 1 hat x plus we have u hat. Now let us say we have one observation here. So if we have this particular observation, so here if we take this and this particular proportion, so this particular proportion is nothing but the estimated y, and this is nothing basically estimated residuals. And what we have, let us say the y bar is here, this is the y bar. Now this variation from this y bar is basically, we are capturing this variation here using this y. So this is the y we have. So this is the total variation of this particular observation from the mean we have. But this variation here is in the two part. One is the residual, another what we have this part, which is basically nothing but the difference between estimated value and this bar. So this is nothing but we have y hat. So this is the total variation. Out of that total variation, estimated regression is able to explain this much variation, and this variation, this estimated regression line is not able to explain. That means this total variation we could write as the summation of the variation which is being explained by the estimated regression or explained by the x, and the another component which is not being explained. So the total variation in the y will be, is nothing but the summation of the variation which is being explained by the x or the regression line, and the variation which is not being explained by the regression line. Now what we wanted to know, we wanted to know how much variation of y is being explained by the x or the regression line. So basically we wanted to find out the relationship between these two here. Now if you are using the summation, we know that some of the observation here will be positive and some of the observation may be negative, and in that case the total sum will be 0. So to avoid that, rather than adding the absolute values, we are squaring that. So let us, for that, let us take the summation here. So summation of y square, then it will be summation of whole square of this, and we will have this particular term. But we know there is no relationship between y hat and the u hat, therefore this particular terms turn out to be 0. So in that case, the total variation, sum of the total variation is nothing but the variation which is being explained by the regression line, and the another term which is basically the variation which is not being explained. So that here we have the specific nomenclature, what we call it the total sum of squares, which is equal to explained sum of squares plus residual sum of squares. Now the explained sum of squares, that is a summation of y hat square, could be written in this format here. Now what is the r square? R square, basically we wanted to know how much variation of total y is being explained by the regression line. So to measure that, it is always better to measure in the percentage term, so that not in the absolute value. So for that what we have done, this explained sum of square, that is the variation which is being explained, divided by the total sum of square, that is the total variation of the y. So that's what we have wrote, and this is nothing but the concept of r square, which basically says that how much total variation is being explained by the estimated regression line or by the explanatory variables. Now this we have, or we know that from the fact total sum square is explained sum square and residual sum of square. So or we can, dividing by the both side, we could have this. And we could write this because this is residual sum is square and this is the total, and this particular gives very interesting result here. Let us say when all the variations in y is being explained by the regression line. In that case, that means u hat, that is residual, will be equal to 0. So in that case, this u hat, summation of u hat square, it will be 0. So the 0 divided by the total sum of square, total variation, will be equal to 0. If that is the case, then this r square turns out to be 1. Another extreme case will be where the regression equation is not able to explain any variation into the y. In that case, all the variation here is equal to the residual. So in that case, the summation of u hat square is nothing but equal to summation of y square. If that is the case, this particular term turns out to be 1. Then in this situation, this r square will be 1 minus 1, that is 0. So that means we will have the two extreme cases when the r square is equal to 1, where all the variation is being explained. Another where we will have r square equal to 0, where nothing is being explained by the estimator. So therefore we can write that r square varies from 0 to 1. 1 being all the variation being explained, 0 being nothing is being explained. Therefore what we can say, higher the r square, that means greater the percentage of variation is explained by the explanatory variables, better the goodness of fit. On the other hand, lower the r square, worse the fit. So that's the basically what we mean by the goodness of fit. Now here the goodness of fit for the multiple regression model. So here we have taken the example of the two variable. Let us see what happens. So here basically we means the proportion of the variation of y jointly explained by the explanatory variables, not by one single variable. So again the formula remains same, and the same formula, only thing here, this explains sum square. For this, the responsibility is for this, all the explanatory variables are responsible for this here. However, once we move from the two variable regression model to the multiple linear regression model, the another concept related to r square we must discuss here. That's known as the adjusted r square. Let's recall that in two variable regression equation we have r square beta 1 hat summation of xi summation of y square. Though in almost every cases we represent goodness of fit by the capital R square. However, in certain cases, in the specific to two variable regression equation model, we could represent this as the R square, because in that case this R squares turn out to be coefficient of determination, square of the coefficient of determination. However, that is the convention we are using. However, in general, we use the capital R square, but specific to the two variable regression model, we could use small r square instead of capital R square. So in the two variable regression model, we have this scenario. However, in case of the multiple regression model, that is the R square, we will have this. And if we generalize this up to the k, then we can write this. From these, what we can observe? If you observe the numerator and the denominator here, as the number of regression is increasing, the terms in the numerator is increasing. So we are keep on adding terms. That means the numerator here is increasing, however, the denominator remains the same. So if that is the case, that means the value of r square will be higher and higher. So from this we can conclude, as the explanatory variables keep on adding, the r square will be more and more, higher and higher. Without the consideration whether the additional variable which we have added is contributing significantly or not. Due to the formula itself, you will have higher and higher R square. Then how to counter to that? Because this is nothing but the basically misleading we have. So to control that, what we do, we adjust the R square with the degree of freedom, and that's why we call it adjusted R square. How we do that? So basically R square we could write this. So here we adjust that with the degree of freedom. So here ASS by divided by degree of freedom, TSS by divided by degree of freedom. Now here we can observe n minus k here, and here we have n minus 1. Now this n minus will always remains the same. However, this n minus k here, where the k is nothing but the number of parameters including the constant. So as we keep on increasing the number of independent variables or the regressors, the number of k will keep on increasing. That means this particular factor will be less and less as we keep on adding. Therefore, the automatic increment is now being taken care by dividing that with the degree of freedom. That's why we call it now adjusted R square. So here, why we do that? Because the R square is not only being used to examine how much it fits. Rather than it is also being used to take the decision among the competing models. If we have the two different models, which model we choose, one of the criteria we do is to pick or to choose the model, relevant model, is we use the R square. However, we know that by being additional regressor there, the R square will be more, so we cannot choose simply based on R square. Therefore, we adjust the R square. Now we can use the adjusted R square to pick the most relevant and appropriate model. To understand that, let us take an example here. So here we are taking example कि saving depends on income. So in that case we have R square 0.50. Now we are adding another variable age, because we know that if age do have impact on the saving behavior other than the income. So in that case R square is 0.51. Now if we have to decide among these competing models, and if we are going to use R square, that could be misleading. Why? Because this increment could be due to just by adding this extra regressor here. Therefore, what we will do, we will go to the adjusted R square. So adjusted R square data is 0.48 and 0.40. So from this it is obvious this first equation fits better compared to the second equation. So based on this, we will make the decision, we will choose this. So that's the basically adjusted R square we are concerned. So what are the properties we have? The first property of adjusted R square is that if n is the large, then there will not be much difference between the R square and adjusted R square. How? Let us take this case here. Let us say we have n, that is the number of observations we have 500, and the number of parameters, that is the k, is 3, then we have here denominator 497. Now let us say if you are adding one more regressor. So in that case, this becomes 4 and here we have 497. Now the variation of 1, it should be 6. So the variation of only 1 does not make much difference in this case here. So that's what we say, if n is the large, then there will not be much difference between the R square and adjusted R square. However, if n is small and k is large, then this adjusted R square may be negative. Why? Because n minus k, if the k is larger than n, then obviously it will be negative, and the overall term could be negative depending on whether this overall term is more than 1 or less than 1. Now, if R square is negative, what does it mean? If the adjusted R square is negative, what does it mean? If it is negative, it does not have any sense. Then basically it implies that adjusted R square is equal to 0. Then the third fact what we have, adjusted R square will never be higher than the R square. Then how we to think of if that by adding the variable whether we will have more higher adjusted r square or the lower adjusted r square, then we can think of by looking the significance of the parameters, which we are going to discuss just after this. So if the absolute t value of the regression coefficient is less than 1, then dropping the variable will increase the adjusted r square. However, if the absolute t value of regression coefficient is more than 1, then dropping the variable will reduce the r square. That means in such cases, by adding the regressor, we will have higher adjusted r square. So that's the difference between r square and adjusted r square. So in case of multiple regression model, we prefer to have adjusted r square rather than the r square. Next, we are going to talk about the significance of parameter estimates. So, using the R square, we have discussed about the overall significance, overall fit of the estimated regression model. However, here what we basically do using the sample, we estimate that y is equal to beta 0 hat plus beta 1 hat x1 plus beta 2 hat x2 plus u hat here. Now, whether these parameters are significant or not, how to test that? For that, we have the two approach. And already we have discussed about the mean and variance of this. That means we have already talked about the distribution of these estimates. Once we know the distribution, then we can devise the strategy or we can formulate the test statistics to examine the significance of these estimates here. So there are the two approaches. One approach is what we know as the standard error test. So a standard error test is basically nothing. Here, basically let us say what is the standard error. Standard error is nothing but the square root of the variance of any estimates. So here we are taking the example of beta 1 hat. So the standard error of beta 1 hat is nothing but the square root of the variance of beta 1 hat. Now, using this, we can make the decision. So, what is the rule of decision we have? Here, the rule of decision is that if the standard error of beta 1 hat is more than half of the beta 1 hat, the value of beta 1 hat, then we have to accept the null at the 5% level of significance. So, what is the null we have? Null, what we have? Null we have this beta 1 hat is equal to 0. And if this is the case, we will accept this null. Accepting this means here this beta 1 hat is equal to 0. If the beta 1 hat is equal to 0, that means there is no significant relationship between y and the explanatory variable x1. On the other hand, if the standard error of beta 1 hat is less than half of the beta 1 hat, that means reject the null. Rejecting the null means the alternate we may accept, that means beta 1 hat is not equal to 0. That means there is the significant relationship between x1 and y, or what we can say x1 significantly affects the y here. Now, smaller the standard error, stronger the evidence against the null. Or we could use the t statistics rather than standard error. So, where what we have t here, t statistics is nothing beta 1 hat divided by standard error of this here. Now, if this calculated t statistics, if it is better than more than the tabulated value of at alpha level of significance with n minus 3 degree of freedom, then we reject the null alpha level of significance and we accept that beta 1 is not equal to 0. That means there is the significant relationship. There is the certain rule of thumb we can share here, that if the number of observation is more than 30 and the level of significance is 5%, and if the t value you have more than 2, then it will be significant. So that means we can reject the null hypothesis. So if the number of observations is more than 30 and the level of significance is 5% and the value of t is more than 2, then we could reject the null and we can say that the beta 1 is not equal to 0, and whatever value we get of the beta 1, that is statistically significance we have. So in this class, what we have discussed about the multiple linear regression model, what is the need of the multiple linear regression model, why we include more than one variable. Then we have discussed the OLS estimates of that. Then we also discussed the properties of those OLS estimates. Then how we use the to test the overall significance, that is how we test the overall fit of the regression model using the concept of R square or the goodness of fit. Then we discuss how to test the significance of the individual parameters. In the next class, we will discuss about the violation of assumptions, certain assumptions. Thank you so much.